Hello. So, in today's lecture, we will be looking at the flow regimes that occur in liquid-liquid flow in microchannels, and in addition, we will also look at the pressure drop in the plug flow regime or in the plug flow. So, as we have seen for gas liquid flow, there are different flow regimes that occur in gas liquid flow in microchannels. Primarily, we have listed as a bubble flow, Taylor flow, or bubbly flow, Taylor flow, slug annular flow, and churn flow. Now, the objective of the liquid-liquid flow in microchannels is quite different in most of the cases, or the application of liquid-liquid flow in microchannels is very different when we compare with gas-liquid flow regimes. The primary objective in most of the applications is to generate monodisperse droplets in microchannels, or to carry out liquid-liquid reactions in very small size droplets. So, the objective here is to create droplet or plug flow. So, in most of the cases, what has happened that the flow regimes that people have analyzed or people have looked at is limited by the velocity or the flow rates in which one gets a droplet or one gets the plug flow. So, most of the cases what one will have is the occurrence of droplet and plug flow. Now, when we compare gas liquid flow and liquid flow, then there are few differences that in liquid flow we have wetting properties of both the phases. So, there are more chances of formation of plugs. That means both the phases might be in contact with the channel walls. Then in the gas liquid flow, the viscosity of the gas phase was negligible, for example. However, in liquid flow, this will not be the case, as the viscosities of both the phases will be non-negligible and comparable. Plus, unlike gas, which is a compressible fluid, both the phases in liquid flow are incompressible. Okay. So, as I have said that there are different applications of liquid fluid microchannels: formation of monodispersed droplet, formation of or production of emulsions, and a large number of encapsulated biological objects, and this is also known as droplet microfluidics. People want to have reactions in small droplets which acts like a small slug reactor and can have efficient mixing because of the recirculations in the liquid plugs or liquid slugs. So, they have number of applications. In addition, say for heat transfer, the gas liquid flow in Taylor flow regime has been used. Why? Because the recirculations, internal recirculations in the liquid slug, they enhance the mixing and thereby heat transfer on a certain number. However, in gas liquid flow, the gas bubbles, because they have very low thermal mass, very low MCP value or rho Cp value. The Cp might be comparable with that of the liquid, but the rho is about 3 order of magnitude for gases lower than that of liquid. Whereas in liquid, both the phases will have equivalent thermal mass. So, immediately when we use liquid flow for heat transfer applications, then a certain number is bound to increase. So, that is another application that people have been looking into for liquid-liquid flow in microchannels. Now, unlike gas-liquid flow, where a number of reviews and a number of papers are available on the flow regimes in microchannels, this is not the case. To the best of my knowledge, there are two reviews available. One is by Zhao and Middlework, where they have reviewed two-phase microfluidic flows, and in that there is quite a bit of section devoted on flow regimes in liquid-liquid flow in microchannels. So, most of the discussion that we will have in this is based on that paper. And the other paper is by Gunther and Jensen in Lab and a Chip by the name Multi-Phase Microfluidics, from which the name of this course is inspired. So, they have also looked at a review of liquid-liquid flows, but very small and short and crisp review about liquid-liquid flow in microchannels. Okay. So, one of the things to understand is that liquid-liquid flow in small diameter channels or in microchannels is dependent on the structure of the channel or structure of the channel inlet. So, gas liquid flows, they are affected by the inlet condition, but not to the extent that is observed in liquid-liquid flow. They are very sensitive to the channel inlet conditions. So, there are a number of different devices that have been used for liquid-liquid flow in microchannels. The three main are T-junctions, flow focusing devices, and co-flowing devices. So, T-junctions, one can have a T-junction where the flow is happening like this. There are two phases coming from two different streams, or another example of T-junction can be that one phase and there the two phases come head on. And so, a variation of T-junction is also Y-junction, where people have looked at the effect of the angle between the two streams on the flow regimes. Then another is flow focusing devices. So, the difference here is that there is the dispersed phase come through the center and the continuous phase come from here, and before that there is a constriction. So, the velocity that it has is normal to the velocity of the dispersed phase flow in the flow focusing devices. Co-flowing devices, on the other hand, have a similar structure, but in this case the dispersed phase again comes from the center and the continuous phase comes from the sides, but the flow is parallel in this case. So, in here we can say the flow is perpendicular or we can say the continuous phase flow is perpendicular to the dispersed phase when phases come in contact. So, in this place the flow is parallel, but when they come into contact, the flow in the flow focusing device, the continuous phase flow become normal to the dispersed phase flow. In the co-flowing devices, the flow is Okay. So now let us look at the flow regimes in these three different configurations. So in T-junctions, there are actually three modes of operation in T-junction. The first one is what we call cross flowing. So we have a T-junction, and in this case the cross flow. So the continuous phase is coming in the straight channel, and the dispersed phase comes from here. So when the dispersed phase come from here, as the bubble generation or the droplet generation in this case will be like this, and the droplets will be moving from here. So that is for cross flowing. In the perpendicular flow, where the channel configuration is same, but now the continuous phase comes from the branch, whereas the dispersed phase comes from the straight channel. So in this case, the dispersed phase will be experiencing a force because of the velocity of the continuous phase, and then it will break off into droplets. The other configuration where we have T-junction, but in a different configuration where we have a T-junction, and the liquids, the two liquids, continuous and dispersed phase, they come from two different arms of the channel, and then they come head on. Now depending on the inertia of the two fluids, probably one of the fluid will enter earlier than the another, and then so this might be the case for other way around. So we can have the dispersed phase breaking around in this case in such a manner. Okay, and probably by changing the flow rates of the two phases, and depending on the hydrophobicity of the two liquids, one can change the continuous and dispersed phase in such a configuration. Okay, so now some of the examples from the literature for T-junctions. So in this case, what is happening? This is from Tice et al., and there is cross flow where the dispersed phase coming from here and the continuous phase straight through. It is glycerol water is the dispersed phase, and FC3283PFO is the continuous phase, and we can see three different flow regimes, and they have named as and the distinction between these flow regimes is coming from the capillary number, three different values of capillary number, which have of course been varied by changing the velocity of the three phases. The density and surface tension, the viscosity and surface tensions are same. So the channel size is 50 by 50 micron square channel, and one can observe the formation of droplets or plugs, or so those plugs, when they say the plug can be of two types, where no contact with the wall and we will be focusing, or we will be saying the plug more to the flow regime where it is in contact with the wall. So in this case, we can see that there is a thin film that separates. Now these three different flow regimes, what is different here that in such cases the breakup in the first flow regime, which they have named as squeezing, the breakup happens just at the T-junction. In the second case, which is known as dripping, the breakup happens downstream of the T-junction, not at the T-junction itself. And then in third case, we see a jet of this liquid coming into, and then a longer neck forms and the droplets form. We can see that the size of the droplet is reducing as we move from here to here in the three cases. Okay. Then another work is due to Thorsen et al. And what they have looked at the flow regimes in a square channel of 60 by 60, and then again it is a cross flow type of configuration. They have looked at in square channels as well as circular channels. So in the square channel, for the what they have specified is the pressures for the two phases, and these pressures, these numbers are in psi. So water pressure and oil pressure, and one has the droplets forming in this case. So depending on the pressure, one always get the droplets, but the size of the droplet, the distance between the droplet, the distribution of the droplets changes with the pressures. In all the cases, the oil pressure is same and the water pressure has been increased. So as we see that water pressure is increased, the droplets are becoming more and more close to each other. Okay. Now the same configuration, but for a round or circular channel for water oil continuous flow, they have got a very different flow regimes in the circular channel, and they have drawn a map based on the pressures of the two phases. So on the x-axis, what is drawn is the average pressure in psi, so oil pressure plus water pressure divided by 2, whereas on the y-axis the difference between water and oil pressure and divided by the average pressure. So basically the pressure differential has been plotted. So when oil pressure is very high, then one see or when oil pressure is greater than the water pressure, then one see only the flow of oil, no water. Then as it is increased, then we see three different flow regimes here, H, B and C. So if we identify these H, B and C, and depending on the pressures and the average pressure values, one can see that there is formation of droplets, and as the size of or as the pressure is increased, the average pressure is increased, the size of this droplet is seen to increase. The water pressure in all three cases is the difference of the two pressures is negative. So that means water pressure is lower than the oil pressure. Now as the water pressure is increased and they are almost equal, then we see few different configurations depending on the average pressure G, J, A, K, E and D. So if we look at A and G, where we have droplets and they are forming a necklace kind of a structure, G and A, and then K again, and there we have sometimes two droplets, and interesting structure that two droplets horizontally followed by two droplets vertically together, again a very kind of regular structure here. And then E, where we have long droplets connected together, and then E, again the droplets of different size. So there are different structures. Very small change in the pressure can change the flow structure, but what we have essentially is the droplets, one or two droplets, and it can be long droplets at higher pressure, at higher pressure we observe when they are both of them are equal, then we have long droplets, but just a small decrease or slightly lower water pressure and one see spherical droplets. So, a number of patterns one can see here, that solid water stream or solid streams, not solid but a continuous stream, what we should say. And then elongated droplets, triple droplet layer. So, we can see that at higher water pressure, where water pressure has increased now, in this case we have F, I and L. So, here we have continuously two droplets with each other in the L configuration and the triple droplets in the F configuration. So, water pressure is higher in this case. Now, so depending on the pressure of the two phases, interesting patterns have been formed in this case. Okay. Now, this is an example for perpendicular flow. So, where the dispersed phase is coming from the straight channel and the continuous phase is coming from the channel normal to it, and then they have different snapshots. The image has been taken from Zhu et al. As described in Zhao and Middelburg paper. So, one can see the two different configurations, the droplet flow, or in this case the circular droplet, and here the long droplet. So, we have a droplet, spherical, as well as Taylor droplet, which look like or which has a shape like a Taylor bubble. And so, this is for recently by Yagonitsaina in Chemical Engineering Journal, they have published their findings, and then they have conducted the experiments in 200 by 200 micron channel and used three different liquid combinations, kerosene, water and different other oils. Now, they report different flow regimes. They have done over a range of flow rates and different liquids. So, they show that they have observed parallel flow, then plug flow. So, this plug flow, you can see that there is no film surrounding the wall, both phases are in contact with the water, and that is bound to happen when we go at smaller channel size, because at the smaller channel size what is going to happen, the contact angle will play a major role, and so the hydrophilicity and hydrophobicity of the channel will also play a role. So, one can have plug flow there. They have termed this flow regime as slug flow, which is different from the notion that we have about slug flow. You may also notice that the configuration that they have is head-on flow, that the two flow regimes comes from the two branches of the T-junction and then they match at the center. The channel size is 200 by 400 micron, and these two channels are 200 by 200 microns. Okay. Then they also get rivulet flow. So, one do not get a continuous phase, whereas one has a small stream of one phase, and then on the other side you have the other phases. So, this is on the wall. So, this is called rivulet flow. And then they have an interesting flow pattern which is called serpentine flow. So, the configuration in 3D that they have described in that it is there are very structured or very regular continuous waves on the two phases, which one might relate with Kelvin Helmholtz instability. So Kelvin-Helmholtz instability is generally seen when there are two different fluid streams with velocities, different velocities u1 and u2. Originally, it was observed for or it was derived for the two fluid streams which are flowing parallelly and the two streams are inviscid. When the fluid streams are inviscid, there is no profile in the two, and then Miles looked at the effect of the velocity profiles on the instability. So the instability causes the waves on the interface, which was originally or which initially had a smooth interface and then it was perturbed. Okay, so this looks very much like the serpentine flow what they described. This might be caused by Kelvin-Helmholtz instability, which might be playing a role there. Okay, then coming to the next configuration, the flow focusing device. In this case, the dispersed phase, as we said, the dispersed phase comes from the center, and the continuous phase comes from the two sides of the channel. And in this case, what is observed that it generally generates droplets rather than plugs. So in the T-junction, we generally see that one of the phases, for example, in this case, the cross flow, one of the phases in contact with the wall. So the wall contact angle is bound to play a role in the generation of the droplets or plugs. Whereas in this case, the separation happens either here or afterwards. So this is the contact with the channel walls can be avoided in this case, and the co-flow devices also. So one observes two flow regimes have been observed in this. One is called dripping flow regime, which is observed at low flow rate. Another one is called jetting regime, which is observed at higher flow rate. So in the dripping flow regime, one observes at low flow rates or at the low velocities, the droplets of uniform size, monodispersed droplets are being generated. When the flow rate becomes higher, then there are droplets of different sizes. Inertia has become higher, and inertia might play a role when these droplets break off from the jet. In the first case, one can get regular monodispersed droplets which are spherical in shape. Okay. Now, this kind of structure where a continuous jet is being broken into droplets, as we have seen, we can relate it with the, say for example, we have all of us have taps in our kitchens, in our bathrooms, and then we see that there is faucet coming out of the tap, and then it disintegrates into smaller droplets, and that is generally attributed to what we call capillary instability or plateau-Rayleigh or Rayleigh-plateau instability. So in this case, what the instability says that a long cylinder, a static long cylinder of liquid, it breaks up into small droplets, and then the lambda at which this breaks up is equal to the 2 pi r of the jet. So the same instability, capillary instability, might be playing a role in this regime, but it will also have the effect of viscosity, effect of inertia playing a role on this disintegration. The similar phenomena also happens in an inkjet printer, where one need to have droplets generating. Of course, there are active actuators also which control the droplet generation in the inkjet printers. Okay. Now, next is co-flowing device. So, as we discussed earlier, in the co-flowing device, the flow happens in the same direction, both the continuous and the dispersed phases. And so in this case, the dispersed phase is introduced by a capillary or by a needle in the continuous phase, and like flow focusing devices, one observe dripping and jetting regimes in this case also, and there are different, one can see that sometimes one get the droplets of two different sizes and the droplets are of a monodispersed droplet. So, this transition between jetting and dripping regime they have attributed to the capillary number, which is basically interplay of mu u over sigma. So, the viscous forces and the interfacial forces. So, in all the cases in fact the T-junction co-flowing and flow focusing devices and any other focusing devices or any other mixing devices for liquid flow or gas liquid flow. The capillary number is the major factor, the interplay of surface tension or the interfacial and the viscous forces is an important factor. So, they have suggested that when capillary and Weber number are small, so when velocity is small, the dripping occurs as we have seen for the flow focusing devices, and then jetting occurs when either of that increases, and then they have given a criteria when capillary plus Weber number is of the order of 1, then one observes the jetting regime. So, if we look at this, the capillary number is the ratio of viscous effects divided by interfacial effects, and Weber number is ratio of inertial effects and interfacial effects. So, when this becomes order of 1, so that what they suggest that when the viscous forces and inertial forces they are equivalent to the interfacial forces, then the jetting regime takes over. In the smaller regime, one would have, or at this lower velocities, the inertia will be negligible. So, and the interfacial forces will be dominating then over the viscous forces. Okay. We have what we have looked at is the different flow patterns that may occur or that has been observed in the literature for flow focusing devices or co-flowing devices or T-junctions. Now, there is another work by Dreyfus et al. Where they have used a flow focusing device, a configuration like this, tetradecane and water. Tetradecane is the dispersed phase which is coming from the center and water from the two sides, and it is in 200 by 200. This is micron, 200 by 200 micron channel, and they observed different flow regimes, isolated droplets, pearl necklaces, stratified or parallel flow, and pear like drops. So, we have isolated droplets seen here, stratified flow which is as that the what is termed as parallel flow, that one phase is coming at the center and the other two phases on the sides of it. And then they have a pearl necklace type, that there are two droplets which are connected by smaller shapes here, and then they also have a pear shaped droplet, different interesting shapes. And this has been done when the channel is wetted, fully wetted. Now, the other case, when they had a that they observed that if the phases are interchanged, then the same regimes are not observed, and then they say that it will depend that the system, of course, this we have already said, that they said that from the flow regimes it depends on the way fluids are injected. So, the system does not forget its initial conditions. It is difficult for the system to forget its initial condition, probably because the viscosity of the fluid is high. So, what they have seen in the previous case that was for fully wetting regime, so it was hydrophilic. Now it is partially wetting, so hydrophobic channels, and then they see that they have observed that well defined structure as was observed in the previous case are not observed. They have observed some stratified flow, but not a smooth one. Some corrugations are there on the interface, and then they have droplets of irregular shapes, as one can see here, they are observed. So basically this is sensitive to the way flow rates are varied and enough stress, what they suggest that enough stress is not generated so that the fluid advects. The capillary number in these cases was of the order of 10 to the power minus 3. So what they have, what is the objective of this, that the hydrophobicity of the channel can play an important role on determining what flow regimes are being generated, everything else being the same. Okay, Gunther and Jensen in their work, they have put together the flow regimes from different researchers in different channel sizes, and then they observed that the segmented isolated drops or the segmented, which is Taylor kind of flow or stratified or parallel flow, and piers like shape have been observed, and this flow regime map they have drawn in for dispersed phase and continuous phase as the coordinates of the graph. Now the next topic in this, so as we have just seen that depending on the hydrophobic hydrophilicity of the channel, one can have that both the phases are in contact with the channel wall. So our general notion of slug flow is that there is a long droplet like Taylor bubble shape, they are moving in the channel. But at lower channel diameters, one may observe, or one as one has observed, some of the researchers have observed that there are plugs of different phases. So you can have phase 1 and then another plug of phase 2 and then plug of phase 3, plug of again phase 1 and then plug of phase 2. So we can color it differently to distinguish the two phases. And in such a case, the contact angle is going to play an important role, and because the interface is moving, so the contact angle is not going to be static, but it will be a dynamic contact angle. So Hoffman proposed an expression for dynamic contact angle, but which was simplified by Weinov and Tanner, which says that dynamic contact angle can be given as a function of a static contact angle and capillary number and a constant A, which has a value of 94 if the angles are in radian. So Ca we already know is mu u over sigma, and theta d is dynamic contact angle and theta s is static contact angle. Now this law, which is theta d cube minus theta s cube is equal to a Ca. If Ca is small, which is generally the case of the order of 10 to the power minus 3, especially for low viscosity fluids, then we can linearize it. So what we can write is that theta d cube is equal to theta s cube plus ACA, or that can be written as theta d is equal to theta s cube plus ACA raised to the power 1 by 3. Then we can write this as theta s into 1 plus ACA over theta s cube raised to the power 1 by 3. Now we can approximate for low CA. We can suggest that ACA over theta s cube will be small, so we can write this as theta s into 1 plus 1 by 3 ACA over theta s cube, or we can have theta d is equal to theta s plus 1 by 3 ACA over theta s squared. So that is the linearized versions of now one need to take into account the sign of the velocity, and as we have seen, or as we know, that CA is equal to mu u over sigma. So for advancing contact angle, one will have a theta d for the advancing case, and u is positive. So one will have theta s plus 1 by 3 ACA over theta s squared. We can put this in terms of theta s advancing. So this is static advancing contact angle, and this is dynamic advancing contact angle. Similarly, when u is negative for the receding case, one will have theta r or theta d receding is equal to theta s receding minus 1 by 3 A CA over theta s receding squared. So immediately one can see that theta d advancing is greater than theta d receding from this expression, if of course the theta d as advancing is greater than theta s receiving sufficiently than this. Okay. So based on this these correlations, now we try to look at the pressure drop when we have plugs in microchannels. So if we have a picture of the plug that we just described, and let us consider one unit cell where we have the plugs of two phases 1 and 2. So this total pressure drop will be the sum of frictional pressure drop plus the pressure drop caused by the capillary force or the capillary action near the wall or by the contact angle. So the frictional pressure drop, if we assume the flow to be laminar and use Poiseuille solution, then we have delta P friction is equal to 8 mu 1 L 1 by r squared plus 8 mu 2 L2 by r squared. So then you will also have u, where u is the velocity of the plug, and both the plugs will have to have the same velocity at steady state. So that is the frictional pressure drop. Now let us turn our attention to the capillary pressure drop. So for the capillary pressure drop, if we analyze one plug, then we will have the interfacial pressure drop, say at the two junctions P1 and P0. So what we will have, the pressure difference at the front is equal to 2 sigma over r curvature, and if we say that this is theta advancing contact angle, then we can draw a geometrical configuration This is the radius of the channel, the angle being theta, and the radius of curvature is this, what we term as r curvature, and this angle is 90 degree. So the angle here is theta advancing minus pi by 2, and this angle will then be theta d advancing minus pi by 2. So what we can write is that sine theta d a minus pi by 2 is equal to r over r curvature. So that will give us minus, so we will have this as cos theta d advancing is equal to minus r by r curvature. So we can substitute that from here, that delta p cap is equal to minus 2 sigma cos theta d advancing divided by r. Similarly, so that is at the front, and the similar expression can be written for the back. So one can have that delta p cap and back of the plug is equal to 2 sigma cos theta d receding divided by r, and that will be, the minus sign will be because of the concavity. So we can have the total pressure drop delta p at cap because of the capillary force is the sum of the two. So we will have 2 sigma over r cos theta dynamic contact angle receding minus cos theta dynamic contact angle, which is for advancing. Now we can recall what we had for theta. Theta dynamic For advancing, we had an expression that theta static advancing plus 1 by 3 a CA over theta SA squared. Now if we take cos of this, so if we substitute this here, then we will have cos theta SA plus 1 by 3a CA over theta SA squared. So that will be cos A plus B. So cos A cos B minus sin A sin B. So cos theta SA cos 1 by 3 ACA over theta SA squared minus sin theta SA into sin of 1 by 3 ACA over theta SA squared. So if we have assumed while linearizing this that ACA over theta SA squared is small, so we can say that cos 1 by 3 ACA over theta SA squared is about 1. Cos 0 we know that it is 1, and at low values sin theta is equal to theta, so we can say that sin of 1 by 3 ACA over theta SA squared, that is equal to about 1 by 3 ACA over theta SA squared. So we can write that as theta. From here we can write that delta P capillary is equal to 2 sigma over R. The same substitution can be done for the receding angle with a minus sign there, and we will get 2 sigma over R cos theta SR, so static constant angle receding, minus cos theta static angle advancing plus ACA by 3 2 sigma over R into sin theta SR divided by theta SR squared plus sin theta SA divided by theta SA squared. And now what we can have is if there is static no static hysteresis, so that means that theta SA is equal to theta SR. So the first term in this will go away, this term will be 0. So what we will have as delta P is equal to 2A over 3R CA into sigma into sin theta SR over theta SR squared plus sin theta SA divided by theta SA squared. Now one can have this the ratio of, just to compare the two force pressures, the delta P capillary divided by delta P the frictional drag. So this Ca into sigma, you can see that Ca into sigma is mu into u. So and if we assume that mu1 is equal to mu2 for simplicity, and L1 is equal to L2, so we can write this as the frictional pressure drop as will be 8 mu L u by r squared multiplied by 2, and this will be 2a over 3 r mu1 u into sin theta SR by theta SR square plus sin theta SA divided by theta SA square. And if theta SR and theta SA are equal, so one will have this substituted by 2 sin theta S divided by theta S square. So mu1 and mu2 are same, so we will have this mu to be cancelled out, 1 of r will cancel out, and we will have this as 8 into 2, so this 2 into 2 will cancel out, and we will have 4 into 3, 12 L theta S squared, and at the top we will have AR into sin theta S. So that will be the ratio of delta P capillary over delta P friction. So one can see from here that if L is smaller than delta P capillary can be significant. So if theta S is equal to, let us say, pi by 2, then this number will be AR by 12 L pi by 2 squared, and then one can where A is 94, so one can estimate what this number is, and one will have that these forces are quite equivalent and the ratio of L by R. Similarly, one can have an magnitude when considering when there is static hysteresis. So the idea here is that that how to analyze the effect of the wall contact angles by the simple Weinhoff-Tanner model, and then appreciate the fact that at low R the capillary force might be important when compared with the frictional forces, and that is what we see in smaller channels. Okay. So in summary, in today's lecture what we have looked at the different flow regimes that has been observed in the literature in different inlet configurations, T-junction configuration, flow focusing devices, co-flowing devices. People have observed the parallel flow, mainly the two flow regimes that has been observed are droplet flow and the plug flow or Taylor droplet flow. And then people have also observed the parallel flow, or what they call stratified flow, and then pearl flow, pearl necklace flow, and so which are generally the droplets which are interconnected with each other or with bridges around them. So different interesting observations are there. Then we have looked at the plug flow in microchannels, where we analyze the pressure drop when there is no film that separates the droplets from the channel wall and the pressure drop in such cases, and appreciating the effect of capillary pressure drop. Now, it has been observed in some cases that at low channel diameters, people also get similar kind of plug flow in gas liquid flow also. So, the same analysis can be applied for gas liquid flow. Plus, when one have say triangular channel or rectangular channel, then the Taylor droplet may not be, it may not have a film everywhere. There might be a contact angle or there might be a contact with the wall of the channel at certain places, especially at the center of the channel. So, in such cases also one need to take into account capillary forces when analyzing the pressure drops in such channels. So, that is all for this lecture. Thank you.